In this lecture, we will discuss moment genetic function of Poisson distribution. So we start the question, that means obtain the moment genetic function of Poisson distribution. Also calculate the mean and variance. So we know that the mean and variance of Poisson distribution is lambda. Mean lambda and variance is also same. So here, first we calculate the moment genetic function of Poisson distribution. So first we write down that we know that the Poisson distribution is discrete probability distribution. So the probability mass function of Poisson distribution so probability mass function of Poisson distribution is P of x is equal to e raised to the power minus lambda raised to the power x upon factorial x, where x is equal to 0, 1, 2, and so on. So this is the probability mass function of Poisson distribution. So lambda is the single parameter. We write an only parameter. Now, so to find the moment generating function MGF of Poisson distribution, we know that the Poisson distribution is discrete probability distribution, so we use the summation. So about origin, so mxt is equal to summation of e raised to the power tx into px. This we can write down as summation of e raised to the power tx into px e raised to the power minus lambda raised to the power x upon factorial x. So again, here we use as x is equal to 0 to infinity. So now when we open the summation, so we write down e raised to the power t into 0, e raised to the power minus lambda raised to the power 0 upon factorial 0 plus e raised to the power t into 1, e raised to the power minus lambda raised to the power 1 upon factorial 1 plus e raised to the power 2t, e raised to the power minus lambda raised to the power 2 upon factorial 2 plus e raised to the power 3t, e raised to the power minus lambda q upon factorial 3 plus and so on. So here first term e raised to the power 0 is 1, lambda raised to the power 0 is 1, factorial 0 is 1. So this gives us e raised to the power minus lambda plus second term we write down as uh, e raised to the power minus lambda e raised to the power t upon factorial 1. Next term we write down e raised to the power minus lambda e raised to the power t to the whole square upon factorial 2 plus next term we write down e raised to the power minus lambda e raised to the power t whole to the power 3 upon factorial 3 plus and so on. So e raised to the power minus lambda we can take as common. So this gives us 1 plus lambda e raised to the power t upon factorial 1 plus lambda e raised to the power t to the whole square upon factorial 2 plus lambda e raised to the power t to the power whole cube upon factorial 3 plus and so on. So we know that the expansion of 1 plus x square upon factorial 2 plus x cube upon factorial 3 plus x raised to the power 4 upon factorial 4 plus and so on. So this is the expansion of e raised to the power x. So this is the expansion of e raised to the power x. So here we replace this x by lambda e raised to the power t. So this is the expansion of, so we write down this is the expansion of e raised to the power minus lambda into e raised to the power lambda e raised to the power t. So we can say that this is our moment generating function. Mxt is equal to e raised to the power minus lambda into e raised to the power lambda e raised to the power t. So when base is same, so we can write down this as e raised to the power lambda e raised to the power t minus 1. So this is moment generating function of Poisson distribution. Now after obtaining the moment generating function of Poisson distribution, we calculate the mean and variance. So we already know the mean and variance of Poisson distribution is lambda. So now for calculating mean, so we know that mu r dash is equal to dr upon dt raised to the power r into mxt at t is equal to 0. So here we put r is equal to 1. So that means first moment we can calculate. So mu1 dash, this gives us d upon dt into mxt at t is equal to 0. So now we write down this as d upon dt. Mxt is e raised to the power lambda into e raised to the power t minus 1. So we put at t equal to 0. So when we differentiate this, so for differentiating, we use this term e raised to the power, we write down this as d upon dt e raised to the power minus lambda we take as this side, and e raised to the power lambda e raised to the power t, and now we write down as t because e raised to the power minus lambda is purely constant. So this we can take outside from the differentiation. So we can write down d over dt of e raised to the power lambda e raised to the power t at t is equal to 0. Now, so when we differentiate this, so e raised to the power minus lambda. So when we differentiate this, so this gives us lambda e raised to the power lambda e raised to the power t into e raised to the power t at t is equal to 0. So this gives us e raised to the power minus lambda into lambda. So when we put t is equal to 0, so e raised to the power 0 is 1, e raised to the power 0 is 1, so gives us e raised to the power lambda. So now we write down this as lambda e raised to the power minus lambda or e raised to the power plus lambda. Base is same, we add the power, so this gives us lambda. So the mu1 dash is equal to lambda. It means that the mean of Poisson distribution is lambda. So mean of Poisson distribution is lambda. Okay. So if you want to differentiate this in another way, so you can differentiate, you can take e raised to power t as x or that function, then you can differentiate. Okay, so we assume that let x is equal to e raised to the power t, so d over dt e raised to the power lambda x. So when we differentiate this, so this gives, we can differentiate this as lambda e raised to the power lambda x into dx upon dt. So dx upon dt means e raised to the power t. Okay. So now we obtain the second moment, mu2 dash. So mu2 dash is equal to d2 upon dt raised to the power 2 into mxt at t is equal to 0. So d2 over dt square or mxt. So mxt, we have e raised to the power minus lambda into e raised to the power lambda e raised to the power t at t is equal to 0. तो एक बार डिफरेंशिएशन तो हम ऑलरेडी कर चुके हैं इसका, तो वो हम डायरेक्ट यूज करेंगे. So this can be written as d over dt and one time derivative. What is our one time derivative? So the one time derivative is, so e raised to the power minus lambda is purely constant, we take outside. And what is the differentiation of this? So differentiation of this is lambda e raised to the power lambda e raised to the power t into e raised to the power t at t equal to 0. So now there is a two function of t. There is two function of t. So this we can write down e raised to the power minus lambda. So when we differentiate this, so lambda again we take outside. So this lambda also taken outside. So now we differentiate this. So the differentiation of this is lambda e raised to the power lambda e raised to the power t into e raised to the power t. Second function e raised to the power t plus e raised to the power lambda e raised to the power t into differentiation of second is e raised to the power t. So now we write down a lambda e raised to the power minus lambda. So when we put t equal to 0, so this gives us lambda or e raised to the power 0 is 1, so e raised to the power lambda. E raised to the power 0 1, e raised to the power 0 1 plus here e raised to the power 0 1, e raised to the power 0 1, so this gives us e raised to the power lambda. So now uh, we simplify this, so this gives us lambda plus 1. So this gives us lambda square plus lambda. So this is our mu2 dash. So this is our mu2 dash. Now we obtain the variance. So when we obtain the variance is equal to sigma square equal to mu2 dash minus mu1 dash square. So mu2 dash is lambda square plus lambda minus mu1 dash. mu1 dash is lambda, lambda to the whole square. This lambda square to lambda square cancel, so this is lambda. So sigma square is also lambda. The variance is also lambda. So mean and variance are same for Poisson distribution.